Hey crew, we're going to take a look in this section. It's lesson 4 of chapter 4. It's again from section 4.6, and we're really looking at how do we determine if a relation is a function or not. So in your notes, again, have your notebook, something to write with, something to write on, and take down that we're going to be looking at is the relation a function and how to determine that using what's called the vertical line test. And then looking at the domain and range for each of these graphs. I'm going to kind of step back a little bit and pause for a moment. If you can write down the title of the section, that it's lesson number 4, and part A, yes or no, is it a function? B, state the domain, and C, state the range. And then here, take a look at setting up a graph in the coordinate plane, and I have 4 points graphed already. And if it's not easy to determine where the points are, I can give you the ordered pairs associated with them as well. Give you a moment to catch up. All right, and again, feel free to pause the video at any point to kind of help you out. So when I look at this graph, I want to know if these 4 points represent a function or not. So in order to help you graph them, I'm going to write the ordered pairs that are associated with them. Our ordered pair is, it's going to indicate our movement from the origin. So I start at 0, 0, and I'm going to go left 3 and up 2. So the ordered pair would be -3, +2. The second point I have here, I start at the origin. I do not move right or left, so that would be 0. And then I go down 1, 2, 3, 4, 5. So down 5. Let's go to this point here, starting again at the origin. 1, 2, 3, 4, and then up 3. So right 4, up 3. And with my last point here, right 4, and then down 2. So if you would, you can sketch this. It doesn't have to be on graph paper. You can freehand it. I put it on the grid board so that it would make what I'm trying to demonstrate as clear as possible. So I have 4 points, and I want to know if those 4 points create a function or not. If I had the mapping picture of it, it would be pretty clear to me. And I think also you guys noticed that when you look at this, I taught you a neat trick, and that is any time if there are 2 ordered pairs that have the same x value, that's going to be a red flag. If you have the same x value and 2 different y values, that's going to be a red flag that it is not a function. So when I look at this relationship, and it is a discrete relationship, these are distinct points. You would have to pick the pen or pencil up off the graph paper in order to graph the next one. So this is a discrete relation. I'm just kind of mentioning that so you can identify the difference between a discrete relation and a continuous relation. So when I look at these points, it's going to jump out at me that these 2 points have the same value 4. So my input is paired not just with 1 unique value, but 4 is paired with 3, and it's also paired with -2. So before going any further, I'm going to be able to say, no, this is not a function. But there's really a neat test called the vertical line test that can do the same thing in a very efficient manner. If I draw a vertical line through these 2 points here, whoops, that's not a very good vertical line, but we'll come back there and go over that. If you draw a vertical line and that vertical line hits more than 1 point in your relation, then you can determine it's not a function. So when you go ahead and look at any of these, it does the same thing because all of the points on this vertical line share the same x value. If you wanted to put some more points on this line and add in, this would be 4. If I add in a point right there, this would be 4, 2, 4, 6, 7. And if I wanted to add another point here, the ordered pair that would be associated with that would be 4, 1. And if I want to put another point down here, this would be 4, negative 4. So notice that every single point that's on that vertical line shares the same x value. When we get into chapter 5, we're going to determine that this is the equation, x is equal to 4, and every single point on that vertical line has an x value of 4. So think about the relation between a vertical line and all the x values are the same. No matter where you draw a vertical line in the coordinate plane, every single point on that vertical line has the same x coordinate, has the same x value. So if you are able to draw a vertical line through your relation and it hits your relation in more than one point, then it is not a function, because that determines very quickly that you have two distinct points that have the same x value, and therefore it is not a function. Because don't forget, a function has to have each member of the input paired with one and only one output. So if 4 is paired with 3, if I do my little mapping here, if 4 is paired with 3 and with negative 2, there's the issue. That input value is paired with two different output values, and that helps you determine it's not a function. I also mentioned in this kind of setup here, is the relation a function or not a function? So we answered part A in this first question, and I'll use the setup to kind of go through problem number 1, and that is this relation a function, yes or no? And the answer is no, it's not. Then I asked you to go ahead and state the domain. Well, the domain is going to be all the values that are my input values. So it's going to be a set of numbers, and it's going to include all my x values. When you list a set of values, you don't have to list the value more than once. So this is 0, 4, 4, and negative 3. 0, 4, 4, and negative 3. But I don't need to list the 4 twice. So 0, 4, and negative 3. That is the set that represents the domain for this relationship. Notice I'm not going to call it a function. I'm just going to say it's a relationship. And I was just making sure that's on screen. And if we want to state the range, it's the set of values for all my outputs. So it would be 2, 3, negative 2, and negative 5. Technically speaking, the order in which you state the set of numbers, it's not wrong if you state it 0, 4, negative 3, but being math people, we tend to be on the organized side. So I usually list my sets from least to greatest, but you can notice I didn't there, and I wanted to demonstrate that you don't have to. We just usually do that as math teachers. So when I list my range out, I'm going to start with negative 5, negative 2, and then 2, and then 3. So I'm going to step out of the screen there for a moment. I'm going to get rid of my vertical line test ordered pairs, because I think that kind of made that point in that mapping, get it out of the way. So what we had were, from the start of this problem, we had 4 points. These are the 4 points. I'm going over them one more time before I move the camera. I went over those 4 points in red to demonstrate that this is a discrete relation, and because these 2 points fall in the same vertical line, it allows me to determine that it is not a function. And then from there, I can state the values from the input values as my domain and the output values as my range. Basically, the x coordinates, the x values are my domain, and the y values are my range. And then I'm going to go ahead and move you guys over a little bit so we can look at a continuous relation. I'm going to go this way. I might even, I'm gonna actually be a little awkward here, but if I move this desk, I'm afraid I'm gonna drop the camera, which is my cell phone, which would be bad news. I was trying to avoid doing that, sorry about that. So I'm gonna kind of see if I can get all of you in there and then get rid of the information I wrote over for example 1. So let's get rid of this and this and this and start all over. So in example number 2, I gave you a continuous relation. If I were to graph this, I would start here and it continues on forever and ever, or I could go like this and then put the arrowheads in it. But there's no break in between this point and this point and this point and this point. They're so close together that it's just continuous. It includes all real numbers on this, and all real numbers can be not easy. They're not going to be discrete like you go from -1 to 0 to 1 to 2. If they're continuous, it includes all of them. So the easiest way to represent it is with a continuous line. So in that relation that we have on the board, I would like you to go ahead and see if you can determine if that relation is a function, yes or no. And can you figure out the domain and the range? It kind of steps it up a little bit in level of difficulty. But let's start with, is this relation a function? And I'd like to use the vertical line test, because if I can draw a vertical line anywhere on this graph and have it intersect the relation in more than one point, it's automatically not a function. So I don't have to do any intense calculations. I draw a vertical line. I notice the vertical line intersects my relation in more than one point. So I'm going to immediately determine that this relation, is it a function for part A? And the answer is going to be no, it's not a function. Then we go to part B, state the domain. That becomes a little more complex. When we want to identify the domain of a relation, it's every value. If I gave you a bunch of points plotted, it's pretty easy to just list out the x values. But when it's a continuous relationship, it's a range of values, so you have to use inequalities to represent the domain. So my domain is going to be all values that have meaning on the x-axis. So if I were to start with this point here, this is the ordered pair -2, 0. So I can notice that my domain goes as far back as -2, and then it continues to the right forever and ever. And it goes on and it doesn't ever stop. So if I look at values on the x-axis, this diagram, this picture, has meaning on the x-axis, all real numbers as we head to the right. So the domain of that relation is going to be all real numbers x, such that x is greater than or equal to -2. It started at -2, and it has meaning everywhere to the right. If I wanted to plot this point, I could go 1 and then up to that point. I could go 0 and then up to that point. I could go, -1, 0, 1, 2, 3, 4, 5. And these arrowheads indicate it goes on forever. It doesn't ever stop. So it heads off to the right to infinity. So my domain is not a set of values that I can list out discretely. It's a continuous relation, and therefore the domain is continuous as well. So the domain is represented by x, and this is red, x such that x is greater than or equal to -2. So I'm going to write that, x such that x is greater than or equal to -2. So that's the notation that's represented. I have to be honest, I've been teaching a lot of years, and all the textbooks that I taught out of used the colon. They used x such that x is greater than or equal to -2. But I'll keep consistency with the textbook that we're currently using, the Pearson textbook. So the domain is all real numbers that have a meaningful value on the graph. So if I go to the left of -2, -3, the graph, this is not a part of the domain. At -3 or -2.5 or -2.1, there's no value. So the domain starts at -2 and it's all real numbers that are greater than -2. The range can even be more complex to understand than even that. The range are all values of y that have a meaning in terms of this graph. So I'm going to rotate you guys so we can look at the range here. The range are going to be values on this graph that have a y value, that have meaning in terms of the picture. So if I look at the y-axis, I can notice that when I went here to -2, I'm going to kind of draw in, I think it's going to have me like this here, the verticals though. So when we're looking at the range, it's kind of a strange way of looking at it. But as I shade in the blue, this point is affiliated with the y-axis with 0. This is a little bit higher than 0, a little bit higher than that, a little bit higher than that. So all of these points have a y value, and if I go up here, this point has a y and a y and a y, and it continues, and this continues on forever and ever. So the range is going to be all values x, such that it's all real numbers. So I'm actually going to just change that range to all real numbers. The range, because this graph continues, it starts at this point and it goes up forever and ever, the range continues to go up and up on the y-axis to infinity, and then it goes down to -infinity. We did cover interval notation, so the range of values for this particular graph is from -infinity to +infinity, or in other words, all real numbers. And then we're going to look at one more. And I apologize because I'm feeling like my explanation there, I'm not sure if that made sense to you guys or not, but I'm going to move on to the third example, and then we may need to backtrack on this explanation a little bit. But in a nutshell, when I'm looking at this continuous relationship, the domain represents all values of x that are represented by the graph. So this original red graph that looks like an absolute value function, or the inverse of an absolute value function, it does start at this point, and on the x-axis, it has meaning for all values on the x-axis to infinity. So it's all real numbers that are greater than or equal to -2. And as far as the range, because the range is here and it goes up to infinity and down to infinity, it includes the entire y-axis. That's why it's all real numbers. So let's try one more, and hopefully I don't go too crazy on the confusion. So let's start again. Let's kind of almost have a do-over at this point and look at example 3, and perhaps I can make this a little more clear. In example 3, we want to first of all determine, is this relation a function? Any vertical line that I draw through this line is only going to intersect that line in one point. So I'm going to start with part A. And part A, is this relation a function? And the answer is going to be yes, it is a function. Part B is the domain. So let's think in terms of, and I'm going to color code this one, I think. I'm going to try a different method. I want to know the values of x that have meaning in terms of this graph. So I'm gonna take the x-axis and draw points from the line to the x-axis. So if I start over here and I just draw and connect this graph to the x-axis all the way until I hit it, and then back up. So I'm just gonna look at that in terms of blue. This graph continues forever and ever. So from, let's say, this point, we can use this as a starting point. It goes forever and ever and ever. So I could continue to draw vertical lines up to the x-axis to infinity. And also, I could continue over here and go to negative infinity. So the domain is from negative infinity to positive infinity, which is all real numbers. So for part B, I'm going to color code part B is going to be all real numbers. And the reason the domain is all real numbers is every single x value, and you could select any x value anywhere on the x-axis, and it will correspond to a point that's on that line. So perhaps that's a better way of phrasing it. Every single point on the x-axis from 0 to positive infinity and from 0 to negative infinity, every single real number that is on the x-axis has a corresponding point on this line. That's probably the best way of phrasing that. And then I'm going to color code and come in with a contrast. And let's go with purple. I think I'll use purple. Let's look at the range. So now we want to know how the y-axis corresponds to this graph. And if we do the y and do the same idea here and connect all these horizontal lines, as I continue, this line goes on to infinity. It goes forever and ever. So I can continue on the y-axis to continue every single real number that's on the y-axis corresponds to a point on that line. So it goes to negative infinity, and the same is true as we go up above that, above this point, and we continue every single point to positive infinity on the y-axis corresponds to a point on the line. So my range, so part C for the range, that's going to also be all real numbers. I don't know if this is a cheat, but if you stayed to the end of this video, any of our linear relationships, every line is a function. Every line is a function. Okay, let's catch myself. There is one exception. A vertical line is not a function. So other than a vertical line, every other line is a function. And the domain will be all real numbers, and the range will be all real numbers. There are two exceptions, and that is the vertical line and the horizontal line. Those two exceptions to the rule that we'll be studying in chapter 5. But other than a horizontal line and a vertical line, all of our oblique lines, the domain will be all real numbers, the range will be all real numbers, and they are continuous functions, they are continuous relationships, and they will be a function. So kind of a lot. My apologies again, and hope that was helpful.